Let's look at boundary conditions. And we're talking about the BCs for D and E. I tell you right now, this is going to be very short, so hang in there. What we're talking about, the interface between two different materials that have a dielectric. So these might be a vacuum and a dielectric. It might be two different dielectrics. It might be a metal and a dielectric, and so on. These are the results. These are the summaries of the different boundary conditions that we're talking about. This is for D perpendicular or normal. This is for the parallel component, and so on. If we look at this one here, notice that it only depends on the free charge. It does not depend on the bound charge. So the discontinuity between D perpendicular or normal is related to the free charge density. The discontinuity between the parallel component at the interface is related to the change in the parallel component of the polarization. The E-field boundary conditions look exactly the same as what we had before. So in other words, the perpendicular or normal component changes related to the charge density at the interface. The E-field parallel to the interface has continuity because this is equal to 0. So these two quantities are equal. Well, what about this sigma? If we have a dielectric, then we'll have bound charge. And remember, bound charge can create electric fields or contribute to the electric field. Instead of just the free charge density, we have to take the sum to give us sigma. And so notice this sigma here is really the combination of these two charge densities. Okay, so let's look at D. We're going to be looking at these two problems here where we have a pillbox and we're going to use Gauss's law, and we have a line integral along the interface where we'll use Stokes Theorem. So let's begin with a situation where we have free charge on the interface and the D and E fields look something like what we have here. The E fields would be similarly drawn here. These are just the D fields. For a Gaussian surface, we're going to take this pillbox. If we make this height very, very small, then we really only have to worry about the flux through the surfaces that you have here. Very similar to what we did before for the E field. So we're going to call this D perpendicular or D sub n, the normal component, and we're going to use Gauss's law for D. And so what that means is there's no epsilon 0 here. It's just the surface integral of D. For that purpose we have the pillbox for the surface. And that's going to be equal to the free charge that's contained within the pillbox. And so that would be the free charge inside along that interface. So we're going to consider the height of this pillbox very, very small, so we can not worry about the sides. Well, realize if we make that small, D is a constant along one of these surfaces. So if we make this small, then D is a constant. That means that we can bring D out of the integral. Let's call the area ds like I have here. Then the dot product of d1 times this minus this dot product is giving us the total integral here. Now why the minus sign? If you look at the surface normal, it's this way for this surface and it's this way for this surface. So d2 you have to put in a minus sign because of that opposition of the directions. What we have here then is that the rest of the equation is the charge contained within the pillbox. We can throw away the area and we're left then with the normal component of D and how it changes. We can call that delta D normal, and that will be equal to the free charge density. So here we go over here. If we dot the D1 into ds, we get D1 perpendicular. It's the normal component of D1. Likewise, we get D2 perpendicular. And that's where we get these two values. And just to nail it, D sub n is the component of D normal to the surface. So restated then, the D perpendicular from Gauss's law gives us that the discontinuity of D across the boundary depends on sigma sub f. If you speak in terms of normal or perpendicular components, that's what we said before. It's discontinuous by sigma f across any surface. Obviously, if there is no free charge at the boundary, then the normal or perpendicular component of D is continuous, because if this is 0, then these two quantities are equal. For the parallel component, we'll use a line path, which is this right here. We could call that lambda. We'll have a D2 here and a D1 here. Again, we make the lines that are along the perpendiculars, we'll take those to be very, very small. So in terms of the line integral, we can ignore these contributions. If we use Stokes' law, the fact that curl D equals curl P because the curl of E equals 0. Let's restate that. D is equal to epsilon 0 E plus P. That's the definition of D. Take the curl of D, you'll end up with epsilon 0 times the curl of E plus the curl of P. But this is equal to 0. What that means then, this is equal to curl of P. Take the surface integral of del cross D dot ds. That'll be the surface integral of the curl of P dot ds. And change that using Stokes Theorem to a line integral. So both sides give us line integrals about lambda, and so we have the D term and the P term. If you look at what we're getting here, because the lambda is tangential to the surface, this dot product is going to give us the parallel component of D. Delta L is the length of this component here, so delta L then is this length here. Because D parallel is essentially constant over this line interval, we can take it out of the integral, and so we end up with the simple condition that D parallel above times the length of that line segment plus D parallel below times the length of that line segment, taking into account that there's a minus sign because of the directionality of DL. It switches. Same goes for the P vector, so we have exactly the same equation for the P, and again we get a minus sign because of the change in direction of the line segment. Divide by delta L, and we're left with the boundary condition that we wanted for the D vector, which is the change in the P vector. All of these are the parallel components. We've derived the two sets of boundary conditions. This is the parallel version, and then here's the normal component version. We've already said for the E vector, the E field, we have the same boundary conditions that we had before, which were this equation here and this equation here, as long as we replace this with the sum of the free charge density and the bound charge density on the surface.